So once we obtain the equilibrium setup, we compute the eigenmode of that using the spectral code, which has a particularity to be able to compute the whole spectrum using a QZ solver or a given eigenvalue, an eigenvector around a shift using an iterative Nordita solver. So the eigenvector finally are known on the Chebyshev grid. And that's, for example, an example of fundamental modes, fundamental radial mode with its eigenvalue is 0.23 and its damping rate. You see that the damping rate here is a growth rate, it's positive. So this mode is unstable for the cation mechanism. Okay. And that's the real part of the temperature for different position of the hole in conductivity or the opacity band. Okay? And then Thomas did a parametric survey of this problem by changing, for example, the temperature of the band and the amplitude of the band for a given width. And what he found instability strip, which means that for given position of the band, modes are unstable. Okay? And for given position of the band, modes are stable. Okay? And the question is why this mode here is unstable, and why we got instability strip, and we wanted to understand the physical mechanism, and the good way to do that is to first work integral. Work integral means where the growth rate is positive in the domain. So it's something like the integration of the eigenvector in the layer. And we see that the real part of the work integral is positive here. It's positive here, here. But the real part is also negative here, here, and here. So that's a competition between the positive region and the negative one. And it's an integral. So at the end, if the positive region wins, the mode is unstable and the contrary is stable. And what we show that, for example, in this case where the hole is here, the work integral is like that, okay, and the mode is stable. When we are here, the mode is unstable, and when we are here, blue, the mode is stable. And that corresponds to the process here, red, green, and blue. And why the mode is unstable for the green case? It is because this quantity is around unity. This quantity is the ratio between the mass, the internal energy, which is above the layer, divided by the luminosity. So that's here. This is the ionization zone. So we take the mass, which is above the layer, divided by the luminosity. This time scale, which is time scale, gives the time scale to evacuate the radiation above the layer. And if this time scale divided by the mode period, this is the mode period, is around unity, it means that there is a coupling between the radiation and the oscillation above the layer. And when this coupling is around unity, the mode is unstable. Okay? And this region here, where this ratio is around unity, is called the transition region. Okay? So the physical criterion for the instability is psi around unity. So that's what we did before doing that in the pencil code. Okay? So let's go back to the pencil code. So what we are doing actually is this one. And what we are supposed to do is this one. Exactly the same, except that we want a convection zone at the top. So to have a convection zone, we just have to decrease conductivity very low to increase the temperature gradient above the adiabatic point. So actually, we are dealing with that. The problem is the radiative diffusion, because the most favorable setups for the instability, for if we want the setup of the such that the radial mode is unstable, the radiative diffusion is around unity of the surface. And why? Because of the condition psi equal 1. Psi equal 1 means that the mass which is above the layer should be very small. Because the unity are small. And then having small masses above means having small density. And very small density means very large radiative diffusion at the top. So we realize that very fast. For example, the time step associated to the most variable receptor is around 10 to minus 5 in dynamical unit, so it's very, very short, too short. So one needs to deal implicitly the radiative diffusion term. That was the conclusion. So actually,
the other alternative is immediately to use radiatively, optically thin radiative transport.
To use the
optically thin, thick and thin, general radiative transport.
Or you can use the radiative package of Tobin.
That would avoid this problem straight away. It's cheap.
Yeah. Actually, what we are doing is to use a semi-implicit approach. It means that, for example, suppose that we have this problem. The temperature is the equation is simply a diffusion equation. So first we discretize this equation in using something like Frank-Nicolson scheme. That means that take the mean of temperature times n and temperature times n plus 1, and we discretize, we separate the x and y part of the operator. Okay. So this operator, for example, the correct expression is this one. We should not forget that the conductivity depends on temperature. So here, Kij means K for the temperature, Kij. Okay. So the first thing to do is to make this approximation. To say that the operator applying temperature at n plus 1 is the same that the operator applied to temperature n plus the derivative of the operator compared to temperature for time n multiplied by temperature increment. And this is a Jacobian matrix. And as we know the relation between K and T, and temperature, which is an analytic one, we can compute analytically the Jacobian matrix. Okay? So this scheme, this decomposition becomes this one. Exactly the same. In fact, now we have Jacobian matrix in x and y direction. So that's, for the moment, that's correct. So we obtain this one. Identity minus dt over 2 dx minus dt over 2 dy time temperature increment equal to dt apply and operator apply on temperature times n. Okay, so we have here a matrix that we should invert, and this matrix is of type n squared by n squared. So that's very large matrix. So we can invert this matrix using a relaxation method or conjugate gradient method. That's we find more useful to apply an operator splitting approach. In this case, operator splitting means that we take this relation and we found that the operator A applied in this one can be factorized in this expression plus some term, truncation error. And the truncation error is dt squared multiplied by the temperature increment. As the temperature increment of this order of dt, this one is over dt3. And dt to the power of 3 is enclosed in the explicit delta 3 error, in the explicit scheme. So this one should be removed, can be removed.
So what do you mean by enclosed?
Enclosed, that means that it's of same order that the error which are made in the explicit time advance.
Not dt to the third, you mean?
Yes.
That's what I was wondering about, or not?
No, but this is just for one time step.
Yes, that's for one time step, yeah.
So if you apply that to a finite interval, you still get second order, right?
This scheme is second order precision, and the truncation error is third order.
So the precision is actually only second order.
Yeah.
Not
So that's one order less than what the explicit scheme has.
I mean, our scheme has third order. That means the error is proportional to delta t cubed.
Yes.
Well, but the error for a single step is proportional to delta t to the fourth, I think. Because if you apply it to a finite interval, you get delta t cubed. So I think it's still that's still one order lower. But
That's fine.
why not?
But we can.
Okay.
So, for the moment, we remove this. So we get this factorization relation. That means that this one, which is here, can be factorized like that, and on the right-hand side, it does not change. Okay? And then, you apply the Rosenberg splitting. Rosenberg splitting means the factorization can be split in two directions. Okay? So the first one in the x direction, so we have to solve this one first. So we have to invert this matrix, but this matrix is of side n by n, not n squared by n squared. So, and actually this matrix is a three-diagonal one. For the moment, we only code that using a second order precision in space. So inverting a three-diagonal matrix is very easy. So in the x direction we have this one, and then in y direction we have this one, and finally the temperature is advanced like that. Now the final question is, where should we put this implicit stuff in the code? And that's not a trivial question. So actually what we do is we advance the explicit physics, and once the explicit physics is advanced, it becomes a source term like that. It means that we compute temperature explicitly, and the source term is the new temperature minus the former one divided by the time step. Okay? And after that, this source term is included in the Rosenberg scale. And then there are two ways to do that. First, half of the source term is added in each direction. So in the x direction we had half of the source term, and in the y direction we have half of the source term. And the second way to do that is to add the source term at the end. So we compute the x direction, y direction, and then at the end we add the source term coming from the implicit method and the implicit one. Explicit and implicit are merged together. Actually, it's given exactly the same result, almost. So this method has been intensively checked on the onset of convection when the diffusion is very large. So Thomas wrote the perturbation equation to compute the growth rate of convection, the theoretical one, and he calculates the growth rate using the pencil coil. And the two growth rates are exactly the same, with this formula and this formula. And then, finally, this last snapshot. That's the result Thomas obtained just at the end of July. It is the first excitation of the fundamental acoustic mode in the box. So after the test on convection, of the convective instability, so here it's the URMS versus time, and you see that URMS is increasing with time. Okay? And that's for density oscillate around the constant value. And then the growth rate actually of this instability is not exactly the same than the one given by the linear stability analysis. So we have to follow the study. But that's encouraging. That's okay.
Questions? I have one about the first part of the talk. Now, to both bodies, axle and organ. Will it be interesting to do the numerical experiment that you have been doing on part of a sphere with the kind of cooling and heating you have, and to look at it and to see what are the kind of things that happen inside?
Yeah.
Would that be an interesting question?
That's the same, this one. Yeah?
Yes, in part of a sphere. Now you are doing it in 2D.
Yes.
But would it be interesting to do it on part of a sphere, not the full sphere?
In a
of course.
sector. You mean in a sector?
In a sector, yes, with spherical coordinate system.
So like between.
Yes, that's what
Say
we
for
can
example
do.
between
Immediate
say
latitudes.
0.321 in radial direction and maybe say 45 degrees in azimuthal direction and maybe a full sphere in phi direction. Would that be interesting to see what happens there?
Yeah, but maybe one problem is that actually I am able to compute the mode of that, the eigenmode of that, but in a full sphere. If you have the sector of the sphere, maybe my spectral code will have some problem because we developed that on spherical harmonics, but spherical harmonics are defined between 0 pi. So maybe I have to add at my spectral code to compute the eigenmode of a sector. That's on the full sphere.
It may probably select only those angular momentum modes which have zeros on the two sides, depending on what boundary condition we choose.
But I think we don't need a sector in this case. It's an equatorial plane, so it
No.
don't. No?
What I mean is, if we want to do a three-dimensional simulation
Yeah.
with the spherical coordinate system, then only the thing we can do is a sector.
Yeah,
We
but
can't do
actually,
axis.
look, this is actually phi. That's not theta.
Yes,
So that we can do.
sure, but that's two-dimensional.
What?
That's
No,
two-dimensional.
but you go in the third
Yeah.
dimension in theta.
And he is not better anyway at the minute. You're also only, you're 2D.
I want to leave for a moment because
Yeah, but I'm saying if we want to go to
Yeah, I
3D,
know.
projecting onto the inelastic mode in 3D is like sport. In 2D it's already quite difficult to project, so in 3D because you increase the quantum number of the mode. You have
But
now
what he's saying is to do this problem in 2D even better is of course to go to certain coordinates and to do it in the plane.
yes, cylindrical. I did
And
that in cylindrical
And then I
coordinate.
would agree that should be better
Yeah.
because you have higher more mesh points
Sure.
and you are on a coordinate mesh.
I did that already
Coordinates.
in cylindrical. Actually, in the entropy modules, this setup is coded also in cylindrical coordinate. But the problem is that we don't have correct upwinding scheme in cylindrical coordinate. And then I obtain wiggles in snapshot, which are not correct.
we can solve that.
Yes, hopefully.
So we have first to code a good upwinding scheme in cylindrical coordinate and also in spherical one to compare with Steiner-Bock simulation. In Steiner-Bock simulation, upwinding is it's okay.
Concerning the star in a box approach, what we're doing to the velocity field outside the star is certainly bad for your modes, but probably one could also just damp, well, what we're doing is we damp all the velocities, which basically means we have a no-slip surface, which is not a good approximation to what to a real star. If you want something that doesn't allow the matter to leave to cross the surface of the star, but does not affect the tangential motions much, then one could just try to just strongly damp the radial component of velocity, but not the full velocity.
That's true, but you know, in this case that's not very important because G mode does not propagate here. They are exponentially damped. So it can be problematic for acoustic mode. If you want to study, for example, the generation of acoustic mode in this case, having a solid wall here can be a problem. But I think it's not crucial for G modes.
How far are you with your implicit solver? Does it work already?
Ah yes, it's true. But actually,
it's not in the code.
it's not in the code because it's really, for example, I can show you. It's quite experimental for the moment. For example,
I think it's a very good thing that we could use generally. I mean, whenever you want to have an actual diffusion term, you need an implicit solver, even though your time set might not be restricted at a given resolution. If you keep doubling the resolution, at one point the diffusion times will dominate. So I think it's a very good thing.
So you see for the moment in run.f90, what we are doing, it's a time advance loop. We first store the value of the field before explicit time advance. We advance in time explicit.
It's 3D array, right?
F. No. In this case, F is F.
Pencil.
It's a pencil, not the F array.
Okay.
Oh.
So, and then we compute the source term like this one, and then we need the density, and then we call this subroutine IDI constant chi or IDI prof chi or something like that. And this subroutine is coded actually, and then we get the new temperature. Okay. And then what I said yesterday, here maybe we should have a generic call to something like called implicit, which gives the value, infinite value, some other field, and the source term.
Yeah.
Something like that.
I think so.
What is this index 4 about? Where does this index 4 come from?
4, because it's an index of temperature.
But that's what the IL&TT is for, right?
No, 4 is because
No, 4 because we are in.
Oh, he's in the
Oh,
plane.
Okay,
Yeah.
2D.
because everyone is.
Sure.
So that's of course.
We are in 2D.
But then F in it is the full field. It's not just the
Yeah, it's a full field. And then we also have new boundary condition for temperature, and we have, I think, it's, yes, in the time step subroutine, Thomas added all the IDI stuff here. So for different value, for different profile for chi, to test with the onset of convection, we first test with constant chi. That's for testing the onset of convection, the growth rate. And then we have the K, so that's the IDI scheme for constant chi. And then we have the one for, so that's a 3-diagonal solver, which is very simple. And we have somewhere the, not here, we have the IDI solver for profile for chi. And you see the problem with the 3-diagonal solver, that because we are periodic, we should use cyclic subroutine. Cyclic subroutine, that means that you have to invert a matrix like that. 3-diagonal matrices with 1 point here and 1 point here, due to periodic condition. And because of that, in fact, we invert 2 times the matrix.
Oh, that can be done correctly. You mean periodic boundary conditions or what they're talking
Yes, periodic boundary condition means that you have a relation to this one and this one.
Sure, yes. But
There's
there's
2 points
yeah.
here.
But that can be done. That's our equation for that.
This is still in login operations.
Yeah, of course. We have done this, of course, in the compact code. We have the same problem.
That can be done only within one inversion? No, actually we are doing that, but we are, because of that, you should invert 2
Yeah,
times.
but that's no problem.
No, that's no problem.
As long as it scales the same way.
Oh, exactly. That's not
If you
really a
change the
problem.
factor in front by a factor of 2.
Yes.
What do you mean 2 times? You do a sweep. Down and up again.
Yes,
Are you
you have
saying
to,
you do
you have
4
to
sweeps
invert
or-
2 times the 3-diagonal matrix.
So what are you doing? Are you doing 2 sweeps or 4 sweeps?
I don't know. It's called cyclic, so where is cyclic? Called cyclic is not there. Cyclic. Maybe. Yes. So we can yes, it's here. Time step. Yes, here. So cyclic, there is 2 calls to 3-dag in cyclic. Call 3-dag, call 3-dag.
Yeah, that's too much.
I read a lot of things on that, and all people had, to my knowledge, do that. To invert a 3-diagonal matrix with cyclic and
No,
periodic
yeah,
boundary condition.
as I said, this is in the old code. We use that all the time. You can even do it for pentadiagonal system.
Oh, you increase maybe the number of
No
check
problem.
marks.
No, but that's not the problem. You can do it in one go.
Okay, so I would like to see
There's
that.
a few more complications. Yeah.
So maybe we should discuss that over
Yeah.
lunch. So thank you, Ingo.